Welcome to SecOcoops, the podcast created by Ben, Moiz, and Sneh, and powered by Cyber Viewpoint.
Welcome to Cyber Viewpoint Originals, the podcast where we decode modern cybersecurity strategies and real-world defenses for today's digital world. In this episode, we're moving beyond alerts and into the shadows. We're talking about advanced threat hunting, the art of proactively finding the attackers that your automated defenses have missed.
So if you're tuning in, you probably already know this, or maybe you suspect it. The standard defenses, the firewalls, the AV, the signatures, they're essential, sure, but they're just not enough anymore.
Not against anyone who knows what they're doing.
Exactly. We have to work from this baseline assumption almost that the sophisticated attacker, they're already inside, they found a way past the perimeter, dodged the basic stuff, and now they're just living there quietly.
That's really the heart of it. Threat hunting is... It's about sending in the specialists. It's the human element, right? Yeah. Systematically, methodically looking for that adversary who's already set up shop.
Not just waiting for the SIM to light up like a Christmas tree.
Precisely. It's about actively checking if your alarms are even working, or worse, if the intruder just snipped the wires without anyone noticing. It assumes breach.
That feels like a really fundamental shift. Most SOCs, they're built around dealing with the incoming alerts, that reactive cycle. How does hunting really differ from that detection model?
Yeah, it's a good question. It really boils down to knowns versus unknowns. Detection, your typical automated system, it's reactive. It works off predefined rules, signatures we know are bad, maybe some known malicious IPs.
Stuff we've seen before.
Exactly. Stuff we've seen and we've told machine how to spot it. And look, that's scalable. It catches the everyday noise, the commodity malware. You need it, but it's inherently limited. It only knows what it knows.
So it's like having a guard who only recognizes faces from a wanted poster if a new bad guy shows up.
They walk right past. Hunting, on the other hand, is proactive. It starts with human intuition, curiosity, a healthy dose of skepticism.
Healthy paranoia, maybe.
Maybe a little bit. It's using expertise to examine data that hasn't triggered an alert. Or maybe even more critical, looking at data that did trigger an alert, but got dismissed, maybe wrongly, because there wasn't enough context. It asks, what if we got hit in a way our tools just don't understand yet?
That sounds less like following a playbook and more like detective work. You need that curiosity, that drive to find the weird thing.
Absolutely. The mindset is key. You need that relentless curiosity, always asking why. Why is this process talking to that server? Why does this traffic pattern look off? Then you need a systematic approach. You can't just wander aimlessly. You need a methodology, like a defined hunt life cycle, to make sure you're thorough.
And you mentioned skepticism, mistrusting the data.
Deep skepticism. You have to understand that adversaries actively try to cover their tracks. They manipulate timestamps, time stomping, they forge user agents. Logs can lie, or at least not tell the whole truth. A good hunter constantly questions the evidence. Is this real? Is it complete?
It sounds like the hunter's own mind can be a battlefield, too. We often talk about attacker TTPs, but what about the hunter's own psychological traps? The biases?
Oh, absolutely crucial. This is where it gets really interesting and, frankly, difficult. We all fall into these traps if we're not careful. Let's talk confirmation bias.
Okay, the tendency to see what you expect to see. How does that bite you in a hunt?
Okay, so imagine you have a hypothesis. Maybe you think, okay, they probably got in using that old web server vuln we patched last month. You start digging, looking for signs of that specific exploit.
Right.
And maybe you find one little log entry that kind of looks like it could be related. Confirmation bias kicks in. You think, found it. And you stop looking deeper.
Even if other signs don't quite fit.
Exactly. Maybe the C2 traffic looks totally wrong for that exploit, or the lateral movement is weird. But you ignore that contradictory evidence because you latched onto the first thing that fit your theory. A good hunter has to actively try to disprove their own hypothesis, not just confirm it.
That takes discipline. What about the next one? Present bias. Sounds like settling too early.
It is. It's grabbing the quick win instead of going for the full picture. So you find malware on, say, one workstation. That's the smaller immediate reward. The pressure's on. Maybe management wants answers now.
So you jump into containment, clean that one machine.
And you feel like you've done something. But present bias means you might stop there. You haven't asked, was this workstation the real target or just a beachhead?
And the attacker might be
already deeper inside. Maybe they pivoted to the domain controller or the database server while you were busy cleaning that one endpoint. Finding the first piece of evidence isn't the end. It's the start of scoping the full breach. You have to resist that urge to declare victory too soon.
Okay, and the last one, overconfidence bias.
Yeah.
Thinking you know it all.
Pretty much. Threat hunting pulls from so many domains,
Mm-hmm.
host forensics, network analysis, malware, reverse engineering, cloud security. Nobody's an expert in everything. But if you're overconfident, you might see some weird network traffic, something you don't quite recognize, and just dismiss it. It's probably nothing. You don't pull in the network specialist. You don't consult the TI feed properly.
And you missed the crucial clue because it wasn't in your specific area of expertise.
Exactly. Overconfidence leads to blind spots. You overestimate your own knowledge and fail to leverage the team's collective expertise. Humility and knowing when to ask for help are vital.
So, to sum up the mindset, be curious, be methodical, and constantly question yourself and the data. Got it. Assuming you've got people with that mindset, how do you structure the team? Who do you actually need on board?
Right, building the team is foundational. You can't just assign hunting as a part-time task to an already overloaded SOC analyst. It needs focus.
So dedicated roles are key. Who's running the show? The team lead.
Yeah, the team lead is critical. They're the conductor. They manage communication upwards to leadership and downwards to the analysts. They handle logistics, make sure everyone sticks to the rules of engagement, super important legally and ethically.
And they translate the technical weeds into business impact.
Absolutely. But here's a common pitfall. If the lead is also trying to do the hunting day to day, they can't effectively manage the strategy, the resources, the metrics. You really need that separation, especially in a mature team. Let the lead lead, let the hunters hunt.
Okay, so who are the hunters? The specialists doing the digging.
You typically need a core of dedicated analysts. First, the host-based analyst. These folks live on the endpoint. They understand Windows internals, Linux systems, Mac OS. They're looking at process execution, registry keys, file system artifacts, memory dumps, tools like sysinternals, Osprey, maybe FTK or Autopsy for deeper dives. That's their world.
Got it. Boots on the ground on the machines.
Exactly. Then you need the network-based analyst. They're looking at the traffic. How are machines talking to each other? What protocols are in use? Are there weird patterns like beaconing? They understand the OSI model, packet analysis, flow data.
So host and network covered. But how do you make sense of what they find?
That's where the threat intelligence TI analyst comes in. They provide the context. The host analyst finds a weird PowerShell script. The network analyst sees traffic to a strange IP. The TI analyst connects those dots. They say, okay, that PowerShell technique and that IP address, that matches the TTPs of APT group X, and their usual goal is Y. They turn indicators into intelligence.
And once they actually find something, confirm a breach, does the hunter then switch to cleanup mode?
No, that's a crucial boundary. The hunter's job is to find and scope. Once a threat is confirmed and understood, they hand it off to the incident response IR team.
So IR does the containment, eradication, recovery.
Precisely. If hunters start doing IR, they stop hunting, they stop looking for other compromised systems, other footholds the attacker might have. The roles need to be distinct.
Yeah.
Now, IR, or maybe network admins, system admins, those might be roles you pull in from other teams or even outsource, creating a kind of hybrid model. But the core host, network, and TI analysts, ideally they're dedicated hunters.
Makes sense. Keep the focus sharp. How does an organization know if they're doing this well? Is there a maturity model?
Yeah, there are models, typically ranging from level 1, which is very ad hoc, maybe relying on external reports, up to level 5, which is highly optimized, proactive, and metrics-driven.
What are the signs you're moving up that ladder?
Key indicators are things like having those dedicated roles we just discussed, conducting regular planned hunt expeditions, not just reacting, and critically, capturing metrics. How many hunts did we run? What hypotheses were tested? How many new detection rules were created as a result of a hunt?
So success isn't just, did we find a bad guy today?
Not at all. A hunt that finds nothing bad but uncovers a major visibility gap or leads to a new automated detection for a sneaky TTP. That's a massive win. It improves the entire security posture. That's the ROI you show to leadership, improving detection and reducing risk proactively.
Okay, that leads us perfectly into the what. If you have the mindset, the team, what's the actual process? You mentioned a hypothesis-driven approach.
Exactly. Hunting isn't just randomly poking around. It follows a defined life cycle driven by hypotheses. This keeps it focused and efficient.
All right, let's walk through it. Step 1.
Step 1. Formulate a hypothesis.
Huh?
This is the core question you're trying to answer. It shouldn't be vague like, are we compromised? It needs to be specific.
Based on what? Gut feeling.
Ideally, no. It should come from threat modeling, from operational CTI, maybe intel, about a specific group targeting your sector. Or it could be based on frameworks like IRP, ATT, and CK, looking for gaps in your defenses against known techniques. For example, we hypothesize attackers are using WMI for lateral movement between servers in our Tier 1 zone.
Okay, specific and testable. And you need to check if you even can test it, right? Data availability.
Crucial pre-flight check. Do we have the logs? Do we have the tools? If not, the hypothesis might be great, but untestable now. Maybe the outcome is improving data collection first.
Assuming you can test it, what's next?
Step 2. Search for evidence. Now the analysts go digging. They use the SIME, EDR, network sensors, whatever tools and data sources are relevant to that specific hypothesis, looking for traces of that activity.
And step 3 is the moment of truth.
Step 3. Prove or disprove. You analyze the findings. Does the evidence support the hypothesis? If not, okay, maybe the hypothesis was wrong, or maybe you need to tweak it, look in a different place, adjust the time frame, you iterate.
But if you do find evidence, if you prove it...
This is where you fight present bias. Don't just stop and declare victory. If you find one compromised machine using WMI for lateral movement, your next immediate step is to expand the scope. Where else did they go? How did they get WMI access in the first place? Map the entire chain, laterally and chronologically, before you jump to containment.
Understand the full extent of the damage.
Exactly. Only then do you move to step 4. Operationalize. This is where IR gets formally engaged for the cleanup. But just as importantly, you feed back what you learned. New detection rules get built for the SOC to catch this PTP automatically next time. New TTPs, new IoCs go to the threat intel team to enrich their understanding. The hunt improves the overall defense. It's a cycle.
You mentioned CTI and MITRE ATT&CK fueling the hypotheses. Let's dig into that. Why focus on TTPs rather than just, say, block lists of bad IPs?
Because IPs, domains, file hashes, those simple IOCs, they're incredibly fragile. An attacker can change them in minutes, sometimes automatically. It's whack-a-mole.
Right.
TTPs, tactics, techniques, and procedures describe how the adversary operates. They're methods. Maybe they always use PowerShell for persistence, or they favor a specific type of C2 channel. These behaviors are much harder and more costly for an attacker to change. Hunting for TTPs gives you more durable defenses. It's higher up the pyramid of pain.
And MITRE ATT&CK helps structure that, gives it a common language.
Precisely. ATT&CK is like the Rosetta Stone for adversary behavior. It breaks down attacks into standard tactics like persistence, lateral movement, and specific techniques like T1053.005, scheduled task, or T1059.001, PowerShell.
So you can map intel to it, map your defenses to it,
and build hunt hypotheses around it. Let's take spear phishing. An email comes in with a link that's T1566.002 phishing, spear phishing link. The user clicks, downloads a Word doc that runs a macro. That macro spawns PowerShell, T1059.001, to download the next stage.
Okay.
A hunter can use ATT&CK to say, okay, let's hunt for technique T1059.001. Specifically, let's look for any instance where winword.exe is the parent process of PowerShell.exe across all our endpoints. ATT&CK gives you that specific behavior-based query to run. It guides your data collection and your search.
It makes it very concrete. And you mentioned the cyber kill chain, too. Is that still relevant?
It's still a useful high-level model, yeah.
Yeah.
Thinking about the stages, reconnaissance, weaponization, delivery, exploitation, etc., helps visualize the attack flow and identify potential choke points where you might find evidence or disrupt the attack. ATT&CK gets much more granular on the how, but the kill chain provides that broader narrative structure.
Got it.
Yeah.
So we have the mindset, the team, the process, but none of it works without the raw material, the data. Let's talk about the data-driven engine.
Absolutely non-negotiable.
Yeah.
You simply cannot hunt without data. Good data. Lots of it. Stored for long enough.
Where do you store it? How do you search it?
You need scalable data stores, like platforms like Splunk, Elasticsearch, Humio, things like that. Places that can ingest massive volumes of logs and let you run complex searches across weeks, months, ideally even longer. If your logs only go back 48 hours, good luck tracing an attack that started last week.
Makes sense. What are the must-have data sources? Let's start with the endpoint.
The endpoint is often where the action happens, so it's arguably the most critical source. You need detailed process execution logging. In Windows, that starts with the native security of NID 4688. A new process has been created.
But there's a catch, right?
Huge catch. By default, 4688 might just tell you PowerShell.exe started. It doesn't log the command line arguments passed to it unless you specifically enable command line process auditing via group policy or another method.
So without that, you see PowerShell ran, but you have no idea what it ran, the malicious script.
Exactly. You see the gun, but not the bullet. Enabling command line auditing for 4688 is probably the single most impactful visibility improvement many orgs can make, like right now.
Okay, crucial tip. Beyond native logs.
Tools like Sysmin are invaluable. Sysmin gives you much richer endpoint telemetry. Event ID 1, process create, includes command lines and hashes. Event ID 3, network connect, shows which process made which network connection. And critically, Event ID 2, file create time.
Why is that specific event so important? Isn't file creation time standard metadata?
It is, but standard file system timestamps, creation, modification, access times, are trivial for attackers to modify using time stomping techniques. They make their malware look like it's been there forever, blending in with legitimate files.
Ah, defense evasion.
Right. But Sysmin's Event ID 2 logs the timestamp from the kernel's perspective when the file is actually created or overwritten. It's much harder for an attacker to tamper with that without already having very high privileges. So if you see a file where the file system timestamp says 2018, but the Sysmin Event ID 2 log says it was created yesterday, that's highly suspicious. That mismatch is a great hunting lead.
Very cool. Okay, moving off the host, what about the network data?
Network data gives you the communication context. Basic net flow is okay for volume metrics, but you really need deeper inspection. Tools like Zeek, which used to be called Bro or Fantastic. Zeek parses protocols and generates detailed logs for DNS requests and replies, HTTP traffic, SSL TLS handshakes, Kerberos tickets, SMTP sessions, and much more.
So not just who talked to whom, but how they talked.
Exactly. Zeek's SSL.log, for instance, can show you the specific cipher suites offered by a client during a TLS handshake. As we discussed, sometimes malware hardcodes a unique, non-standard list of ciphers, finding multiple internal machines using that same weird fingerprint to talk to an external IP. That's a strong indicator of a common implant, something Zeek helps you find. You also need logs from things like IDSC systems, like Suricata for signature-based alerts, and ideally full packet capture, PCAP, in key network segments, though that's storage intensive.
Understood. And the third bucket, general logs, what fits in there?
This covers a lot. Classic web server access logs, Apache and Jinx IPACs, are still vital for finding web shells or C2 over HTTPS. DNS server logs are critical, looking for weird query patterns, long domain names, signs of tunneling. But increasingly, especially in cloud environments, it's about infrastructure logs.
Like cloud provider logs.
Yes, things like AWS CloudTrail, Azure Activity Logs, Google Cloud Audit Logs. Who's spinning up resources? Who's changing permissions? Also, container orchestration logs. Kubernetes API audit logs are absolutely essential if you're running K8s. If an attacker compromises a container, their next step is often hitting the K8's API to try and escalate privileges, access secrets, or launch more pods. Hunting those API logs is key for cloud-native environments.
Wow, okay. So the data foundation is huge and diverse. Assuming you have decent data, let's get into the really advanced stuff. How do hunters find threats designed to blend in, like C2 channels using jitter?
Ah, yes. Beaconing with jitter. The classic way to evade simple statistical checks. Standard deviation calculations get thrown way off by those randomized sleep times.
So how do you beat it?
You use a slightly more robust statistical method, the interquartile range, or IQR. It sounds fancy, but the concept is simple.
Walk me through it.
Okay, you take all the time intervals between the C2 check-ins for a specific connection. You sort them from smallest to largest. Then you find the 25th percentile value, Q1, and the 75th percentile value, Q3. The IQR is the range between Q1 and Q3, essentially, the middle 50% of your data points.
So you're basically throwing out the extreme highs and lows, the jitter.
Precisely. You're filtering out the noise, the outliers that the adversary intentionally introduced. Now, you calculate the standard deviation only on the data points within that IQR. Because you've removed the jittery outliers, the standard deviation becomes much, much smaller, revealing the underlying regular beacon interval the attacker was trying to hide. It's a neat statistical trick to cut through the noise.
That's clever. Are there other non-time-based patterns you look for?
Definitely. Sometimes it's about consistency where there shouldn't be any. For example, seeing thousands of connections from an internal host to an external IP, and every single connection transfers the exact same number of bytes, say precisely 845 bytes up and down.
That's not normal web browsing?
Not at all. Normal traffic varies in size. That kind of rigid consistency often points to a hard-coded value in an implant's communication protocol. We also hunt for those specific, non-standard TLS client cipher suite lists we mentioned, Zeek can log. Finding that same unusual fingerprint from multiple clients is a very durable indicator.
Okay, moving beyond statistics, machine learning. This feels like the frontier. When do you use unsupervised versus supervised ML in a hunt?
Good question. It depends entirely on whether you already have a good idea of what bad looks like. Use unsupervised ML, like carry means clustering, when you don't know exactly what you're looking for. You're asking the machine, show me what's weird in this data.
Finding the unknown unknowns.
It's exactly. The algorithm groups similar data points together into clusters based on features you define. You, the hunter, then ignore the huge clusters as probably normal activity. You focus your investigation on the small, sparse clusters, the outliers that the algorithm couldn't group easily. That's often where the novel C2 traffic or the weird data exfiltration hides. Maybe it finds traffic going to 40.87.160.0 on port 23456. It just doesn't look like anything else.
But getting the data ready for ML is a big step, right? Feature engineering.
Oh, huge. ML algorithms need numbers, not raw logs. So if you're analyzing, say, DNS data with unsupervised ML, you need to extract numerical features first. Things like the length of the requested domain name, FQDN, the number of dots, the character frequency distribution, the ratio of numbers to letters, maybe calculate the Shannon entropy of the domain name.
Entropy, like randomness.
Yeah, high entropy often indicates data that's been randomized or encoded, which can be a sign of things like domain generation algorithms, DGAs, used by malware, or data being hidden inside DNS queries for tunneling. After clustering, you also need ways to evaluate the clusters, like silhouette analysis, to make sure the weird cluster the machine found is actually mathematically distinct and worth investigating.
Okay, so unsupervised ML is for exploring, finding anomalies. What about supervised ML?
Supervised ML using algorithms like random forest or XGBoost is for when you do know what you're hunting for and you have examples of it. For instance, say you want to specifically hunt for DNS tunneling activity.
You need examples of good and bad DNS traffic first.
Exactly. The absolute prerequisite for supervised ML is having a reliable, labeled training data set. This is your ground truth, where previous DNS queries have been accurately labeled as either normal or tunneled. You engineer features like domain entropy, query length, record types, etc., and then you train the model to recognize the patterns associated with tunneling based on your labeled examples.
What's the risk if your training data isn't great? Maybe you only have a few examples of tunneling.
Big risk of model bias. If 99.9% of your training data is normal, the model might learn that the easiest way to be accurate is just to predict normal all the time. It'll miss the actual tunneling because it didn't see enough examples of it during training. You often need techniques like oversampling the minority class, the bad stuff, or using specific algorithms designed for imbalanced data to make supervised ML effective for rare security events.
It sounds powerful, but definitely requires careful setup. One more technique before we get to takeaways. What about when data is just bad or missing? Deception.
Yeah, deception technology like honeypots or honey tokens is a fantastic way to flip the script, especially in environments with poor visibility or against really stealthy attackers.
How does it work in practice?
You intentionally plant decoys in your environment. Maybe a fake file server that looks interesting, a seemingly sensitive database, or even just fake credentials, honey tokens, stored somewhere an attacker might look. These decoys have no legitimate purpose. No normal user or process should ever touch them.
So any interaction is instantly suspicious.
Instantly high fidelity. The moment anything in automated scan, a curious attacker interacts with that decoy RDP server or tries to use those fake credentials, you get an alert you know you can trust. It turns the tables. Instead of you searching haystacks for needles, the needle jumps out and waves a flag. It's great for detecting lateral movement or reconnaissance attempts you might otherwise miss.
A clever way to create guaranteed tripwires. Love it. Okay, this has been incredibly detailed. For listeners who are thinking, okay, I want to try this, what are maybe one or two concrete, actionable things they could start hunting for today?
Great question. Start simple. Focus on common techniques.
Okay, actionable takeaway number 1.
Focus on anomalous process ancestry. Look for weird parent-child process relationships. A super common one attackers use after phishing is getting Microsoft Office to launch a command shell. So hunt for instances where winword.exe or excel.exe or outlook.exe is the parent process of cmd.exe or powershell.exe. Use sysmin event ID 1 or even properly configured 4688 logs. Legitimate use cases for this are rare and usually known, like specific macros, so anything else is suspicious.
Easy enough to query for. What's number 2?
Hunt for obfuscation in web logs. Attackers love hiding commands, especially for web shells, using encoding. Scan your web server access logs, Apache, IC, etc., for requests with unusually long query strings, or requests where the URI or parameters contain chunks of URL encoded characters that when you decode them turn out to be base64 encoded strings.
Base64 often hides PowerShell or shell commands, right?
Very often. Look for these long, obfuscated requests going unexpected places, like PHP files sitting inside an uploads or images directory. That's a classic web shell indicator. DTP T1827 obfuscated files or information.
Good one. And maybe a third, focused on tooling.
Leverage existing tools. Verify event 46888 auditing. We mentioned it before, but it's worth repeating. If you're in a Windows environment, go check right now if you have command line process auditing enabled for event ID 4688. If you don't, enabling it is probably the highest impact, lowest effort improvement you can make for hunt visibility today. Seriously, do it.
Excellent practical advice. We've gone from the essential mindset shift to building the team, through the structured hunt process, the critical data sources, and even into advanced stats and ML. It's a lot.
It really is. And the core message, I think, is that threat hunting is fundamentally human-driven. It's about creativity, curiosity, and constant iteration. That cycle of hypothesis, test, learn, operationalize it never really stops.
And you have to be okay with failure, right? Not finding anything.
Absolutely.
No.
Resilience is key. Many hunts won't uncover an active breach. But if a hunt leads to finding a misconfiguration, closing a visibility gap by getting better logging, or developing a new detection rule, that's still a huge success. The goal is continuous improvement of the security posture.
Which leads to a really interesting final thought. We focus so much on finding the attacker activity, the evidence of compromise. But maybe the biggest win is finding the vulnerability before they do.
That's a powerful point. Imagine a hunt where, maybe as part of reviewing code deployments or scanning legacy systems, a hunter stumbles upon an old, forgotten API endpoint. Let's say it's patient soul string .patented, and it turns out to have a critical SQL injection flaw.
Something no alert would ever fire on because it's not being actively used or attacked yet.
Exactly. It wasn't found by an alert triggered by an attacker. It was found proactively, as part of a hunt, just assessing the environment's risk surface. Finding that vulnerability, that misconfiguration, that insecure legacy code before an attacker discovers and exploits it, that prevents the breach entirely. That might be the ultimate, often unsung value of a truly proactive hunting program, stopping the fire before it even starts.
That wraps up this episode of Separate Kicks Boops, powered by Cyber Viewpoint. If you enjoyed this deep dive into threat hunting, stay tuned for more episodes where we unpack the most effective strategies shaping modern cybersecurity. Until next time, stay curious and happy hunting.